All right, so we're going to continue on. And by the way, for homework 1, you have all the tools you need. Homework 1 basically is up to the stuff we covered yesterday. It's basically shooting stuff. So you're going to write your own shooting routine, do some stuff with it. That's what you'll do. All right. So today we're going to talk about other things, how to solve boundary value problems a different way. So shooting is just one way. So let's write down our generic differential equation as we had before. Here it is. This is what we considered last time, is something like this with some kind of complicated boundaries. Let's say and then here it is. This is the differential equation. We have these boundaries. And so what we talked about is how to solve this by basically launching from here. Okay? So you have this condition, plus you make up another one. You make up the other one with the purpose of basically trying to hit this condition. That's the shooting method. And then you iterate and get the solution to converge. Okay? So we successfully demonstrated that in class. On Wednesday, you have a little MATLAB code. You can even just copy and paste out of the notes. It works beautifully. Okay? And so now what we want to do is think about other techniques for solving this. So I'm going to do a little simpler version of this to demonstrate the concept. And here's the simpler version we're going to do. We're going to make this thing linear. I'm going to write it like this. Second derivative is equal to, we're going to make a linear differential equation, non-constant coefficient. Now, if you took a differential equations course, okay, here's what you would recognize is to say, hey, linear, that's good. I maybe have a shot at it, but really you don't, unless P and Q are like constants, or maybe really simple functions. This is the part that, this is the reality that you have to work with. Your number of analytic techniques that you have available to you are minuscule. And you have been biased in your education to think you can solve all kinds of stuff. Okay? Because, you know, we've spent all this time, look, you can solve this one and this one and this one. Yeah, as long as they're constant coefficient. Okay? So understand that the world generically, if you have a more complicated problem, you're just, this is why you're in this course. Presumably, right? Except to maybe come see my orange sunshine tie. Because you can't get any sunshine outside. You come here and say, look at that. That's like sun. Okay, so I'll try to wear my yellow and orange as much as possible for you. Okay, but there you go. You have this, linear, and you can't solve it unless, so for generic P and Q. And here we're also going to assume that maybe I have these boundary conditions. It's alpha and beta at the two endpoints. Okay? So there it is. Setup of the problem. Now, what can we do with this? Now, we could certainly shoot across, write this as a first-order system, launch across, try to go from here to here. I'm going to give you an alternative technique for doing this. So first of all, let's go back here. I got derivatives. I got second derivatives. I got to do something with these. This is what we did before, is to say, let's write this as a first-order system and then use my stepping algorithms, use the definition of derivative to get myself a stepping algorithm to go across. Here, I'm going to do the same kind of thing, but we're going to do it a little bit differently. So let's take a function, and I told you there's one calculus trick that you need to know, and that was Taylor series. Yeah, that's it, right? Taylor series. So let's do Taylor series. And I'm going to show you the magic of Taylor. Okay. So let's just do the following. Take a function, expand it around, so evaluate it t plus delta t, and expand it around f of t. Okay, so let me write down the Taylor series around f of t. Well, it's f of t plus, right, delta t times the derivative, df dt, plus delta t squared over 2 factorial, second derivative. And these are going to evaluate t plus, and what we're going to do is truncate it. So right now what I'm going to do is say, okay, the last term here is delta t cubed over 3 factorial, third derivative. And this is evaluated at, let's call it C1. C1, some constant, which I do not know, and it's between t and t plus delta t. But I'm guaranteed to have this. That's an exact result. No approximations have been made. Okay? It's just that I don't know what C1 is. Okay. Now I'm going to do the same thing for Taylor expansion around t minus delta t. Okay? So let's do this. If you do t minus delta t, notice what happens. Well, you just, wherever you see a delta t here, and just make it a minus delta t. That's the easiest thing to do. So you get f of t, delta t becomes a minus delta t, df dt, plus delta t squared, that's minus squared is minus 1 squared is plus, right? So that stays the same. Okay? Minus delta t cubed, 3 factorial, C2 dt cubed. Well, now C2 is some constant, again, I don't know what it is. Set between t and t minus delta t. So there we go. We're just using Taylor expansion. So this is all Taylor series is. If you know one of these formulas, you have all you need to know to be successful in this class. Everybody believe that? I hope. It's kind of true, right? Well, I'm saying that because I'm sitting here and I already did the homework. But it really is true. This is the whole theoretical foundation of everything we're going to do. One of these formulas. Okay? Now watch. Watch. You ready? Nothing up this sleeve or that one. We're going to do something simple that everybody feels comfortable with, even this early in the morning, even if you haven't had not your coffee. I have, but perhaps you have not. And we're just going to ready. You ready? Add. No, actually, I don't want to add. Do I want to? I want to subtract. Subtract. I'm going to take this and subtract that from it. Okay? Everybody go with that? Take this, subtract this from it. I have two simple formulas. Let's go ahead and do this. So I get f of t plus delta t minus f of t minus delta t. See how awesome I did? I just subtracted it like it was nothing. Okay? F of t minus f of t. Cancel. Do you love canceling stuff? You should, because I just canceled that by subtracting them. See, that's why I subtracted them, because I could cancel them. I canceled these. I subtract this from this. Delta t dt minus a minus becomes a plus, right? So I get two of these, two delta t's, df dt's. Let me put the t in there. And I check this out. Subtract those. Cancel again. I know. Awesome. See how I pick easy problems to do on the board? I only have two models in life for teaching. By the way, for those of you who can be teachers in the future, and I always try to repeat it. Do you know what they are, Haley? I think you probably do. No? Don't do algebra in public. Okay? And don't spell in public. Seriously. If you take anything away, you go people home. Don't do. Those are the two things you never do, because you are going to make mistakes somewhere, and you're going to be halfway through this big calculation, and you're like, room of silence, nobody's helping you out, you'll be embarrassed. But if you just don't try to do algebra, except for like this simple algebra, okay, there you go, write that down in the notes. Okay. And by the way, these cancel, so I'm left with this minus minus, gives me a plus. Well, so now this becomes a plus, so I have a delta t cubed over 3 factorial, and then I have that one and this one, so I get, I'm going to write third derivative with primes like this because I'm running out of board space. So at C1 plus f triple prime at C2. What did this buy me? What I'm going to do now, I'm going to solve for df dt here. So I'm going to take this to the side, divide by 2 delta t. Okay? So what do I got? Well, then, so what I have is the following formula. df dt, valued at t, is equal to that, okay, plus delta t squared, bless you, over, I got a 3 factorial and this factor of 2 there. So let me put the 3 factorial here, and let me take the 2 that I divided by and put it here. This is kind of like an average of these two terms. This term plus this term divided by 2. It's kind of like an average. Let's just call it that. F triple prime at some average. And there's my formula. Ready? Ready? How important is it? Oh, look, I put a box around it. That's how important it is. What does it tell you? My derivative, df dt, is equal to f at t plus delta t minus f of dt minus delta t, or f at t minus, did I say? Oh, anyway, my derivative, let me say that again because I kind of got confused in my sentence. It's the point in front, delta t, t plus delta t, point behind, t minus delta t over 2 delta t, plus a little bit of something here, delta t squared. And this is simply rise over run. Isn't df dt a slope, right? So when you thought about calculating slopes in your life, and you didn't think you'd have to do that until you got to calculus, right? And you start thinking, oh, there's this thing called a slope, and I can calculate it. It's a derivative. And the way you thought about it was that it's just rise over run. And so when you think about evaluating a function, you know, if I want to calculate the derivative here, normally we think about just, you know, drawing your tangent line. But the tangent line, remember, is a derivative. It's this thing that has this divide by 0 quantity. We're not doing divide by zeros. So the way I approximate my derivative is by saying I can take the point in front minus the point behind over the run, right? It's delta t. This is the run. Here is 2 delta t. And I basically take those neighboring points to calculate my slope.